So this question is about Hall probe, and it states as a constant current is maintained in a long straight vertical wire. A Hall probe is positioned at a distance r from the center of the wire as shown in the figure. So in this case, the coil has a magnetic field which passes through the Hall probe. So this red line shows the magnetic field strength of the wire. So as the current and the distance is not varying, so the magnetic field strength which passes through that Hall probe is not going to get varied. So the question says, explain why when the Hall probe is rotated about the axis, the Hall voltage varies between a maximum positive value and a maximum negative value. So normally we write Hall voltage as VH equals to BQV. But this is actually a simplified formula, because in all such derivation we assume that the Hall probe is always vertical. The plane of the Hall probe is always vertical to the magnetic field, so sine theta is always 90. But this sine theta, if it's not 90, we should write it as sine theta. So none of the quantities in BQV is going to vary. Only the theta, which is the theta between the magnetic field and the probe voltage, like the probe plane, between the magnetic field and the plane of the probe. Right now the plane of the probe is vertical and the magnetic field is in a horizontal plane. So that angle between the plane of the probe and the magnetic field varies. So when we vary the angle, like we rotate it by 360 degrees, so if theta changes by 360 degrees, that we rotate it by one complete round turn, so we know that sine theta will vary from +1 to -1, right? Actually starts from 0, then goes to +1, like, but in this case we're starting it from +1, then it goes, when it is in the same horizontal plane, it goes 0, and then it goes like -1, and then it again goes 0, and then it again goes 0. So that's at, right now it's at 90 degree. When you rotate it further, at 180 degree it's 0, at 270 degree it's -1, and at moving to forward to 360 degrees, it's again 0. So starting, if we write at 0, it will be 0. So that's why it varies, right? So we have to mention that the dependency of the VH on theta, right? And as theta varies, sine theta varies, is right? From +1, that is going to be the maximum value, to -1. So that's the answer to this part. So moving to the next part. The next part says the maximum Hall voltage VH is measured at different distances r. Data of the VH and the corresponding value of r are shown in the figure. So now they just vary the r. They make the Hall probe move away from the coil of the wire. So as it is moved away, so VH is given by this factor. So this says that VH is inversely proportional to R, because K is a constant. So we can say that VH is inversely proportional to, like we can write VH is equal to constant, K is a constant, and we can write it as constant into 1 by R. So where K is the constant. So now the question says, without drawing the graph, use the data to suggest whether the expression is valid or not. So if the K is constant in this statement, K is actually, if we rearrange it for K, K is the product of VH and R. So the product of VH and R must be the same, no matter what's the unit, because K can be described in any unit. So if we multiply the first thing, have a look, we get to 0.29 into 1 is 0.29, that's right. 0.19 into 1.5 is 0.285, which we can write as 0.29. Again, 2 into 0.14 is 0.28, which we can write, okay, we write it 0.28. 0.097 into 3 is 0.291. And 5 into 0.6 is 0.30. So yes, this value approximately fall as a constant. It varies, like you can write it as 0.29 plus minus 1. So the constant has this value, plus minus 0.01. So it's a constant value. So yes, the statement is right. So what's the answer? The product of V into R is a constant. So hence the above statement is right. So we checked it from the data, that is a constant. So that's why it's the right thing. So moving to the next part, a graph showing the variation of 1 over R. Be careful, it's the variation of 1 over R with 1 over R of VH. So as we vary 1 over R, how VH varies. So that is plotted. State which feature. So if we reconsider the equation, VH, and I write it as K into 1 over R. So this is actually VH is proportional to 1 over R. VH is proportional to 1 over R. So it's a directly proportional graph because we have no constant y is equal to mx plus c. So if we want to compare with this thing, the c is 0. So that actually shows that graph must pass through origin. So this feature of the graph tells us the graph passes through origin. So this feature tells us that it's a directly proportional graph. Got it? So let's move to the next part. The Hall probe shown in the figure A on the top is now replaced with a small coil of wire connected to a sensitive voltmeter. The coil is arranged so that its plane is normal to the magnetic field, like the first position of, as we have shown in the figure, field of the wire. State Faraday's law of electromagnetic induction and hence explain why the voltmeter indicates a 0 reading. So Faraday law of electromagnetic, the induced EMF or the voltage, we can write it as negative n delta phi by delta t. So rate of change in flux. So they just said that as shown in figure A, so it's not rotating. If the coil is not rotating, although the flux is maximum, but it's not changing, right? So a constant flux, maximum but constant. A constant maximum flux at the vertical position. A constant maximum flux at vertical position, like they have mentioned. So a constant. So if it's constant, it means delta phi by delta t, the rate of change in flux is 0. So as this rate of change in flux is 0, this means the induced voltage, or whether you write it V or E, is going to be 0. So moving to the third part of the statement, like the last part of this question, is state 3 different ways in which an EMF may be induced in the coil. So one, by rotation, is right. As we rotate, the flux changes through the coil due to the direction of the plane, is right. The second, by varying the current. If we vary the current at the same point, And the third thing is that as we move the coil toward or away from the wire, because the magnetic field strength depends on the distance from the wire. So as we move the coil toward the wire, magnetic field strength increases, and as we move it away from the wire, the magnetic field strength decreases. So if there is a change in magnetic field strength or the flux, there is a change in EMF, like there will be an EMF induced. So that these are the three ways in which we can induce the EMF in the coil. So that's it for this question.